pleasure to be here in Brazil giving these lectures. So the topic of my lectures will be stochastic optimal control problem, but today I will start with the deterministic case. So I was thinking about the contents, and I don't know exactly what are your expectations from this course. So I have a part of my lectures where that will be mainly focusing on some theory, and another part of my lectures are on numerics. So if you, I don't know, who is interested in the numerical parts of stochastic and deterministic control. Okay, so today what I will do is to focus on the deterministic case. I will try to present the main points in this topic, and then if you agree, the second half of the lecture we can try some numerics together, okay? So I'm from Ensta-ParisTech, which is an engineering school, and now it's a part of a huge university called the Paris-Saclay, gathering many units in south of Paris. Doesn't seem to work. So this is the outline of the talk today. I will talk about control differential systems. Then I will present the first and the most natural approach, numerical approach. And then I will also talk about the parameterization by the control variable. I will make this clear in a moment. So this is what I call a control system. A control system is a system that you can, on which you can act by control. I'm also fixing the notations here. So this is, we have a system. This system will be described by differential. Today it will be described by differential equations. Tomorrow it will be stochastic differential equation, but the most simple one is when you have, you are acting by the mean of control variable that I will call here u, u. And then you have the outcome of this system is what we call the state, and the state will be denoted in my lectures by y. Sometimes I will denote it x, but usually it will be y. So what we want to do here, this is not like a black box. I will show you in a minute. What we have here is something that we know. We know how to describe the model. And what we want to do is given some initial configuration of the system, we are trying to find the best control, u, that can allow us to reach some prescribed performances. So we want to optimize, the performances, and we would like to reach some final state. Okay, so we have a set of constraints on the control, on the state, and we would like to optimize. So here I said many things. I said performances, which means that we have a functional cost, and we have some constraints, and we would like to optimize. So basically, it can be seen like an optimization problem. But by its nature, it has something specific because there is a link between the control and the state. And this is what we're gonna try to exploit for this specific control problem. So usually, the box, as I told you, is not a black box. It describes something that's evolved in a simple situations like that. We have simply a differential equation where f is the dynamics, and u here is the control at time t, and we have the state at time c. So the dynamics may depend also in time, but just to make it simpler, I prefer to consider just this framework. So we have this equation which link the control and the state, and now we want to optimize a performance, which is a cost The cost can be something that depends on the initial and the final conditions. It is also something that's a distributed cost that depends on the trajectory and the control at each time. So this is a general framework, but of course you can also add more costs. For example, if you want just to focus of a part of the trajectory, so depending on the problem. So now the constraints, usually you have a set of constraints on the control itself because you are not allowed to do all the actions you want. And the state in many applications, they are also constrained. So I write the constraints in this form. And usually you may even have some constraints linking the control and the state. Okay? Besides, you may have some constraints which are depending only on the initial and the final positions of the trajectory. So you may have, depending on the problem, you may have different kind of constraints. I think on this slide it's quite general. So usually the control is a measurable function. So the spaces L infinity, L2, it's not important. What I would like to focus is the control is something that can jump. It's just a measurable function. You don't expect the control. You cannot say the control is continuous. While in the setting I'm considering here, the space for the trajectory is nicer, and it's even better than just continuous. So usually we deal with continuous trajectories, unless you have hybrid systems or impulse systems or something very general. But in the setting I just show you what we expect is a measurable control that can jump from one value to another, and the state is continuous. Okay? So please, if you have, don't hesitate to interrupt me if you have any question. Okay? So this is the simplest and also the oldest problem in optimal control theory. It's a Goddard problem. So if you go in a museum in Washington, you can find many things about this character Goddard and his problem. So this is the first problem in the theory, and it's about some rockets. So h, for example, is the altitude here, v is the velocity, and m is the mass. It's a very simplified model for a rocket. So what we want to do is to act on u. So this is just h dot dot is equal to, it's like acceleration. It's equal to mt is equal to some force that is acting on the rocket minus a g, which is more or less the it's just the gravity. Yes, thank you. So here we have m, that's the acceleration is equal to the sum of the forces. Okay, so basically this is the equation we have here on these two lines, and this is the motion of the mass because we are burning some ergol, and this ergol depends on u. So u, it's the thrust, and it's the control. So this is the function that we are acting on, and for each control u, we have a trajectory, which here represents the trajectory for the altitude, for the velocity, and for the mass. Okay, so this is one simple example where we have a state in dimension 3, and the control is in dimension 1. But they are functions of time. So the thrust is constrained by these inequalities because it's always positive. This is so if we just stop this thrust, it means that the rocket will just crash. And it is bounded by a certain amount because we cannot go more than this value. This is the capacity of the engine, if you want. So the mass of the rocket also satisfies some constraints because we have the structure, for example. We are allowed to burn the ergol, but not the structure itself. So the mass should satisfy some constraints. And the optimal control problem in this setting is just to go as high as possible. So to maximize the final altitude, while the control is in this, at each time, is in this interval. And the state and, oh, sorry, there is a mix between English and French. So the state and the control are, they are connected by this simple differential, ordinary differential equation, and this is constraints, state constraints. This is a constraint on the state. This is really the most simple and the first optimal control problem studied in the literature. And it's appeared in this period of the 60s where there was this space race between Russia and United States. So what I will present today is mainly the Russian school, okay? And tomorrow I will start the School of United States. So up to today, the problem is still of interest. So the problem becomes much more complicated, and what people are looking for is a problem which is more elaborated. So, but basically it's still the same. So what we have is, we represent the state. This is, for example, the case of Ariane 5, one of the French or European launcher. So the state variable in this problem is the position and the velocity. And still, with the Newton law, we have this differential equation. So the differential equation which link the state and the control. The control is U. It could be the thrust force. It could be also some angles that we can choose. But when you write the Newton law, you get immediately the equations. So they came from just from some physical modeling. And we still now, people, they understand that they have to take into account more constraints, for example, height flux. There is also limited capacity of ergol. This is was already in my first, in the previous slide when I said that the mass has to be in a certain, it is connected to these inequalities. And we have some target constraints. We are not trying just to go as high as possible. We would like to reach some orbits. And why do we want to go to these orbits? It's because they bring to these orbits, they steer some satellites. So this is the idea. You have this place here on the launcher where the satellites are put, and basically now the problem is still of interest, because to steer, let's say, about 18 or 19 tons of material, they have to spend more than 700 tons of ergos, which is too much. So the problem is still of interest. And now this is the example of Ariane 5. We can come back to it for some numerical simulations later. So, is there any question? No? Okay. So now some more notations and some assumptions. As I told you, the control is usually constrained to be in a set U. So here I note this set U. And U hat is just the set of admissible controls, which means that, okay, so U is a measurable function taking values in capital U almost everywhere. So I will always suppose that this set is a closed set. And about the dynamic, I will assume that it is always Lipschitz continuous, at least. And I would need also another assumption about the convexity. Okay, so I'm dealing with an optimization control problem, and I would like to show you exactly where the convexity here plays a role. But the only convexity assumption that I will need is this one. The convexity of the image of f, x, u. So the set of actions should be a convex set. So these assumptions are important just to have a well-posedness of the problem. So the two first ones are important just to ensure that for any control U, admissible control, you have a trajectory. So this is not exactly like a Cauchy problem, okay? Because U is not continuous, it's a measurable function. This is what we call Kara-Theodori differential, Kara-Theodori solution. So what we have is a Lipschitz continuity and just measurability with respect to time. But the Kara-Theodori solution exists for this equation whenever you have f Lipschitz continuous, for example. So this is very well posed, and the trajectory is absolutely continuous. And also this application that's associated to each control one state, one trajectory, is very well posed, and it is continuous. Okay? So this is just to make it clear. The two only assumptions we need is just to have Lipschitz continuity of f, and that's it. And now I am, since we are considering trajectories, I introduce this notation. This notation means the set of all the trajectories that comes from x that's in the initial position. Okay? So it means that all the trajectories for which there exists a control such that y is a solution of the differential equation associated to this control u, and the trajectory is starting from the position x. Okay? So I introduce this notation because I can see the optimization problem like an optimization over a set of trajectories. Okay? And actually, this set of trajectories here where the convexity will be important, it's here. If I assume that we have this convexity assumption I introduce here, E2, then this set becomes a compact set. So which means that it's a compact in W11. I don't know if you are familiar with these spaces. W11, it's, okay. W11 of 0 capital T is functions in L1, 0t, and such that the derivative in the distribution sense belongs also to L1. And actually, it happens that this set is included in C0t. It's it's better than continuous. Okay, so the function is in L1, and more importantly, the derivative, in the sense of distribution, is also in L1. Yes, it's when you say phi belongs to L1, it means that the integral between 0 and capital T of this function is finite. Okay? But this is even better than L1. It's not only integrable, it's a continuous. So the set of trajectory is compact is really a very important fact, because now you take any continuous cost function and you just minimize over this set of trajectories, and you are ensured that there is a solution. Okay? And also the set of the set valued function that associate to each initial position, this set of trajectories is something very nice and very smooth. It's Lipschitz continuous. This is not, it doesn't need the convexity. The convexity is needed here. And the result that I'm writing here is called in the literature Filipov theorem. Okay? So it's a small but a very nice result that from there you can get the existence of trajectories. So why the convexity is important? Let me, yeah. Not today, but yeah, for Filipov theorem. So maybe one can see the book of Winter's book. But I can give the references later. So what I can do is maybe to put the references on my slides and distribute tomorrow the slides. Okay? Okay, so let me now just show a simple example where the convexity is really important. So I consider the case where we are minimizing this integral between 0 and 1 of the square of the trajectory. The trajectory, y, satisfies this very, very simple differential equation. Y dot is equal to u. And we are starting from 0. The control is not, so it's in a closed set, but it is not a convex one. And now if you, so what we want to do is just to minimize this L2 norm. And the control we are allowing just to act with -1 and 1. So the trajectory, so if we, for example, if you consider this sequence of functions, so un is equal to 1 on half of the interval and -1 on the other half of the interval to, so maybe so it's between 0 and 1. If we consider some intervals between 2k over 2n and 2k plus 2 over 2n, then what we would do is just to consider 1 and -1, 1 and -1, 1 and -1, and then the trajectory that is associated here is something like that. It's just some oscillations. So if you consider this sequence of control functions and the corresponding sequence of trajectories, you can see that the infimum actually is equal to 0. While 0 it's actually is not possible because y equal to 0 is not an admissible trajectory. Y equal to 0 would be the solution to the state equation where we take u is equal to 0. But 0 is not a feasible control. So this is why the problem doesn't admit a solution. We have here a minimizing sequence that goes, the value goes to 0, while the limit y is equal to 0 is not admissible, and this is just because we had a lack of convexity. So if we have convexity here, everything would be solved. This is just a simple problem to show you that the convexity is very important here, not exactly of the control set, but mainly of f x u. This is the requirement. This is what that should be convex set. Okay, so usually when we don't have a convexity, then we convexify the problem, and it's related to what is called in the literature relaxation by Young measures. So there is a huge literature on this topic. But just to make it simple, I will always assume that we have this convexity assumption satisfied. So it is satisfied, the minimum exists, and what we want to do is to compute this minimum or to characterize it. Okay. So if we want to optimize, I told you there is a first method, natural method, that would consist of discretizing the control problem and putting it in the form of a finite dimensional optimization problem. And you are experts in optimization. Once the problem is in a discrete form, then you can use your tools and solve it. So how can we discretize the problem? Usually, so our time horizon is 0 to capital T. So what we can do is to consider a discretization of this time integral. So for example, we choose a number of time steps. Hk would be the duration. It could be constant, or it can be something that depends, adaptative, for example. So hk is the duration of the km time step. So we start at time t0, and the time tk is just the summation of the steps hj. Okay, so we have then, instead of having an interval of time, we now have just some times tk, and we have a finite number of times. We have just n plus 1 times. And now for the state equation, instead of considering this differential equation, we can just consider a discretization. So the discretization of a differential system, it's can be done easily. I don't say that this is the most appropriate discretization, but if you want to just to try first, you can consider the Euler discretization, which is a simple one. And then we have a cost function. The cost function, we had the final cost plus something I didn't wrote here. Can now complete this line. So the cost is something that depends of the final cost, plus instead of this integral, we may have a summation like a quadrature formula, each k L. The simplest one is this one. But of course, discretization of control problem is requires usually to be careful about what you do with what you choose for the discretization of the differential equation, and also how you approximate the cost. But if you want just the simple cases, is you have Euler formula, and this is the most simple approximation for the integral cost. And then the constraints, you consider that you have the constraints only at time tk. So you have finite number of constraints. And everything now becomes in a finite number. So you end up with an optimal control problem where you are in the finite dimensional space. So before we go further, I would like just to mention that some control problems, they are naturally well described in the discrete setting. So the examples I showed you earlier, they were dealing with these rockets or launchers. So very sensitive motion. So you have to act on any at any second, and even at any time, you have to act on the rocket to have the desired performance that you want to reach. While in some examples, it doesn't make sense to act all the time. You can act daily, monthly, but you don't act at every time t. So the problem naturally is described by controlled discrete dynamics. So if you are in this situation, your control problem is just an optimization problem with a very specific structure that link the state to the control, but it is in a finite dimensional space. In other cases, the control problem should be considered in a finite dimensional space because, as I said, for example, the trajectory is very sensitive to the control. So this is just one remark before we go ahead. For example, this production problem that you can find in the literature, this is also one of the oldest problems. Production problem, you have an amount of steel produced at time t. A fraction of steel, the control is a fraction of the steel that is allocated to investment. And we know that the part that is allocated to investment would increase the capacity of production, so we have a simple differential equation in this form. And the aim of this problem is to choose the control in an optimal way to maximize the production allocated to the consumption during the time interval capital T. So which means that in this problem, what we want to do is to maximize. So what would be the cost here? Can you guess? Sorry? The integral between 0 and t. Yes? Y of t. I would say 1 minus ut. This is what you meant. Yes. Because this fraction UTYT was already invested in the production. It was allocated in the investment. And what is left is this part, okay, that we can gather. And this is the production that we can sell, for example. So what we want to do is to maximize this. This is also a very simple problem where k is some coefficient that increase the production. So we have the initial A, and u of t is just between 0 and 1 because it's a fraction almost every time in the time interval 0 capital T. So this is our problem. But actually it doesn't make sense to consider this continuous sitting because I don't believe that in this production problem they can really have a policy at every time. I think they can act every day, every month, every week, but not at every time t. So the problem really should be this one. Instead of an integral, one should consider is just the summation from k going to 1, from 1 to capital N. Here we should consider something like that, and the trajectory should be in this form. Yk plus 1 is equal to yk plus, sorry, my notation is capital K for the coefficient, uk, yk, and h. Here should be just the time horizon that when you can really act on the control. So maybe 1 day to 1 week, I don't know, something like that, depending on the policy. Okay. And here it's for k bigger than 1. So in this situation, for example, you can study the control problem in the continuous sitting. But actually, the problem makes more sense if it is considered in the discrete one. For other problems, it's not the same. And people who are studying these numerical approaches for optimal control problem, this is the questions they try to answer. So now we are no more in the discrete sitting. We come back to the continuous sitting. And what we want to do is to use this simple method, discretize and then optimize. So this is very natural, but the question is to know how is the discretized version is related to the continuous original problem. So for example, if you have a nominal solution, and I say local solution because we don't know if there is only one global solution or if we have local solution. But anyhow, consider one solution, u bar, y bar, of the original problem, and then consider the discretized version of the problem. Let me call the discretized solution is UH-YH. So the problem is to know if this solution is close to the nominal one. And also the second question is to expect the order of convergence. Can we expect something like O of H? Can we have something even more precise? The other question that we can consider is how can we discretize the control? Can we assume that the control is constant on each time step? Or can we consider that the control is something linear, piecewise linear, or piecewise polynomial? How can we choose that? And actually, if you assume, for example, that your control is something that you can interpolate, somehow you are assuming that the control is piecewise smooth, okay? But this is not true. The solution is not always like that. And of course, the last equation is to know how to solve the problem that you end up with. So I cannot answer all these equations in 1 hour and a half. What I can do is just to show you some examples where you can guess the difficulties, okay? So the first example is called in the literature double integrator, the simplest system, dynamical system, coming from Newton's law. Acceleration is equal to external force, okay? So this force U is your control. This is something acting on the system. And Y is just the position and the velocity. So in this graph, we have here the position, and here we have the velocity. So what we want to do is to minimize time. We would like to minimize time to reach this target, which is 0. So we would like to bring the system to a stable equilibrium, which is 0. And if you can actually write everything and show that the problem, this is the solution depending on your initial conditions. So for example, if you start somewhere on this branch, then you can use just the control equal to -1, and you can reach the target. This is the optimal time to reach the target. If you start from this branch, you can use one control equal to 1, always equal to 1. And let me see. Yes, this is what you do. So the velocity is negative. This is the velocity, this is the position. So what you do first, here you can just use the control equal to 1, increase your velocity, and automatically you will reach the target in a minimum time by using this single value of the control. Anywhere else, you will have to commute from one value to another. So if you start, for example, somewhere here, you have to first increase the velocity until you intersect this branch, and then use the control -1. So first increase the velocity, and then you can lower it. And if you, in a symmetric way, if you start somewhere here, you use the control -1 to decrease the velocity, and then you can take care of the position by using the control 1 when you intersect this branch. So in this example, you can analyze the minimum time function and analyze the optimal control that allow you to reach the target. And in this very specific case, the solution is either y of t equal to 1. So this was the case in this in this branch, -1 in this branch. So this is the forms that the control can take. Equal to 1, equal to -1, the third form is something like that. You start by -1 on a certain interval, 0t1, and then you switch to the value 1. Or you start by the value 1, and then you switch to -1. So depending on the initial condition, the optimal control has one of these 4 forms. Okay. So what happens if you use now, so by the way, the solution has the name of bang-bang optimal control. When you take just the extreme values, and we have just one switch in time. So if we analyze any discretization of the problem, one can show that the error is at most O of H. Why? Do you have any idea why it should be O of H?
Because at the point when you switch from -1 to 1, for example.
Absolutely. Yeah, this is the error you would make. Exactly. The error that you would make if you discretize the problem, and you can actually, it's a very good exercise. Usually to the master students, I ask them to do this exercise, just to write down the discretized form and show that you can also have a synthesis of the control depending on the initial state. And you can see that it mimics this behavior. You have some regions where the control one would be a solution, -1, switching from -1 to 1, 1 to -1. So the error, it comes here just because you are switching from -1 to 1 and you are making an error on a small interval h. This is the best you can do, is to get an error of capital of O of H. So I'm not saying, so if you discretize and now put just a time step exactly on the switching time, then you are lucky. What I'm looking at is the error for any h, and it behaves like O of H. You cannot have better than that. So this is something I took from this paper by Bayer, Gertz, and Lempieu, published in 2012. Another example that I took from a PhD work that you can find also on the internet of Julien Laurent Varin in 2005. This is another very simple control problem. It's still the double integrator, but now what I'm integrating is not the minimum cost, is this L2 norm of the trajectory. So very simple. Actually, everything here is convex, but the main issue is the discretization. So Julien did some simulations where he tried to penalize this constraint. Okay? So it's an optimization problem. Then he tried just to penalize this very simple. And he showed that there is a very strange and very complicated behavior called in the literature Fuller problem. Fuller problem is when you have this chattering in a finite time interval. So what he did, he just played with the discretization and the penalization parameters, and showed that depending on when you, if you don't choose very carefully the penalization parameters and the discretization, then you end up with some solutions that have this Fuller behavior. Okay? So this is also one of the difficulties we are facing when we consider a control problem. If you want just to discretize and use the optimization machinery without knowing anything about the problem itself, then you can get a solution which is far from what you are expecting. Okay? So this is the message of this slide. Okay, and other examples are known in the literature. So it answers just some of the questions I put on the slides. On the slide is about the order, if the trajectory is smooth or not. And actually, the answers are not very clear, because in many situations, even if the problem is a very simple one, we have numerical solutions that are not very convincing. So just to sum up about this discretize, first discretize and then optimize approach, I would say that this is the most natural and the most general method that you can imagine. It can integrate all types of constraints. You can discretize any kind of constraints, mixed constraints, state constraints, control constraints, anything can be handled. At least on the paper, okay? When you write the problem, you can include any constraints you want. And of course, when you discretize the problem, and this is very important, you have a finite dimensional optimization problem. And on this topic, there is a huge literature. So there are many softwares, many methods that can be used here to solve this finite dimensional problem. So what are the inconveniences? So the inconveniences, there are many. First, when you discretize and use an optimization problem, then usually you have just a local solution. It could be a problem for some applications where you want to obtain really the global solution. When you discretize, you also have a huge number of variables because you have to discretize the control function, the state function, and all the constraints. Then you may end up with a very complex and a problem with a huge number of variables. A more serious problem, I know that's a huge number of variables. It's doesn't really scare you as experts in optimization, but sometimes it can be an issue. And also the more serious problem is the stability and convergence. As I showed you earlier, if you discretize even a simple problem without knowing what is going on in this problem, if you don't know what is the structure of the control and the solution, then you may not have the convergence. So you solve a finite dimensional problem, and when you let your time step go to 0, maybe you don't converge to the solution of the original continuous problem. Okay? You can have bad convergence, but you can also have no convergence at all. Yeah, to guarantee the convergence, sometimes you really need to know more about the optimal trajectory, but sometimes you don't have informations available on the optimal trajectory. Sometimes you do have available informations that you can guess from the physical problem, and then you can use this information to perform a discretization that is suitable for the problem. Okay, so now we have a choice. I can continue now with the theoretical part, or I can show you, we can come back to this Goddard problem and try to see together how we can discretize it and solve it. What do you prefer? Yes. So we can move in 30 minutes. I can continue with some...
It's up to you. You are the boss.
Okay, it depends on the audience.
When they don't answer my...
For me?
My strategy is that I choose. So you choose.
I choose. Okay, so... Okay. Then I choose. I will continue a little bit more about the theory, and then the second half would be in the lab. Yes, please, do.
Can you discuss a little bit about this other approach, discretize and optimize versus optimize and discretize?
This is the second part.
Okay.
Yeah, this is what I call here the parameterization by the control variable. but it means that we first optimize and then discretize. So first optimize and then discretize means that you have to do everything. So what you know in optimization theory, first in the infinite dimensional space, all right, your optimality conditions, discuss these optimality conditions, and you discretize once these optimality conditions are provided. Okay, so this is what we can do. I will start maybe by a simple discrete case where we can write everything on the blackboard, and then I come back to a more general setting. Okay. Oops. Sorry. So let me now consider just this simple control problem in a discrete time setting. And I assume that UK belongs to capital U for K going from 1 to N. Okay, so we have just a final cost, okay? I assume that the distributed cost is 0 for the moment. And we write this problem. So this is an optimization problem in infinite dimension. We have n variables for the control, n plus 1 variables for the state, and that's it. And we have, this is our state constraint. So if I write now the Lagrangian, this is what we do. Then I can write the Lagrangian like that, introduce Lagrangian variables, pk, uk, minus, okay, I'm not allowed to go behind this line. Minus yk plus 1. Okay, this is the usual Lagrangian with the Lagrange multiplier p. So I introduce this one. So now assume that this is from 0 to n minus 1. Assume that we have a solution y bar, u bar, then there exists p bar such that the derivative of the Lagrangian with respect to y is equal to 0. And the derivative with respect to u with respect to y minus u bar is positive for any control u admissible. By admissible, it means that the admissible means that we have a vector of n values that are chosen in capital U. Okay? So now let us exploit this information to get a characterization of the optimal solution. So if we derive with respect to y, for k equal to 0, we have an information that p0 with p0 plus, I'm just using differential calculus, plus h0 f prime of, sorry. No, I think here it's more convenient for me to do that. Okay. The Lagrangian, I take it in K+1 because I know that it simplifies things later. Okay, so for k is equal to 0, I end up with p plus 1. Alors, plus p k plus 1 h0 f prime y 1 y0, yes, thank you. U0. This is equal to 0. This is the first equation. And for any k, I would have, if I discretize, if I derive with respect to k, I get pk plus 1 plus hk, pk plus 1, hk, f prime, yk, uk, and I get another contribution minus pk is equal to 0. So this is what we get for any k greater than 1. Okay? So for k equal to n, I will get Pn. So Pn minus 1. Pn, when I derive with respect to yn, I would get phi prime un minus Pn plus 1 equal to 0. So this is what we get if we derive with respect. I'm sorry, but I prefer to put everything on the blackboard just to show you how the computations are done. And now there is a magical trick that appears here. The magical trick is that you can now write this equation, this one, also in a dynamical form. So we have pk minus pk plus 1 over hk. It's equal to f prime yk uk that pk plus 1. So this is
Hasnaa, there is in that equation there is an hk inside and an hk outside. You have to erase it here.
Oh, it's a mistake. Yes, I put it outside here. Okay, thank you. So this is the form, and we have Pn is equal to phi prime yn. plus 1. Thank you. No, here it's n. Okay. So this is what we call in optimal control. It means that the constraint linking the control and the state is in a dynamical form. And the Lagrangian multiplier has also, it follows this dynamic. So it's not exactly the same, but it's not exactly the same equation, but still it involves the derivative of the dynamics f with respect to y. And we have also a dynamical system connected to this Lagrange multiplier. Now, if I write, if we want to exploit this inequality, then we get, if we derive with respect to the control, we can see that pk f by u, uk, uk u minus uk should be positive for any u belonging to capital U. So this is what we get if we derive the Lagrangian with respect to the control. So this is if we use the derivative of the Lagrangian with this value uk, then we get this information. Okay? So this is what now I will try to get in the continuous sitting. Is this clear for everybody? Okay. So the most important thing here is that we can use the general framework in optimization, introduce the Lagrangian function, then use what we know in for an optimal solution. We know that we have this condition satisfied. This is the first optimality condition. And then if we exploit this information, we get a specific structure for the Lagrangian, okay? The Lagrangian multiplier. And now I want to do the same for the continuous sitting. So I will use basically the same thing. Here we have an optimization problem where, again, I consider that we have a dynamical system, ODE, and we have an initial condition. I add here a final condition, but basically it's the same calculations. So if we consider that the application that's associated to each control trajectory, this is well defined, sorry again for the French words. This application is very well defined, and the optimal control problem can be seen now. Everything you can, so I told you that you can see the control problem as an optimization over sets of trajectories, but you can also see the problem as an optimization problem over just the sets of controls. So the trajectory would be hidden in this application, okay, in this map. So to each control, you have something that is implicit, but well defined, and you can see the optimization problem like that. Now, if you have a minimum, then you know that you have this optimality condition, and I wrote here the optimality condition in not in a normal form, meaning that since I don't know if my this constraint is qualified or not. So the state equation is well defined. So now if I consider this problem, the only trouble can come from here, okay? This is from where the trouble can can arrive is this final constraint. And so if we don't know if the constraint is qualified or not, then in the general setting you have a multiplier lambda 0 that can be 0 or 1. This is just the general theory of optimization, okay? Optimization theory. So this is if lambda 0 is equal 1, this is nothing else than just the derivative of the Lagrangian is positive. This is, but if lambda 0 is equal to 0, it means that your constraints are linked and you don't have the qualification of the constraints. So when I wrote this formula, derivative of the Lagrangian, one can wonder if this map, capital T, so I said it's well defined, it's continuous, but you can wonder if it is differentiable or not. And it is. It is, and I prefer to write what this differential, the derivative is, because it's a very important in control theory. If you derive on a control U and you apply to another control V, this is what people in robotics and in control in general call the linearized state equation, okay? And you can prove this result very easily just by considering, for example, the state T U plus H minus T of U divided by H. And you can see that at the limits you get a function zeta that depends on U and V and is solution to this linear equation. I just forgot to say that this is true, of course, if the dynamics itself is differentiable, is C1. Okay. Sorry? You start with the control U and then you modify, you just linearize the states. So, and you can see that the trajectory, that if you, yeah, you start with the U, you perturb, sorry, this is what I meant. Yeah, if you start with the control U, you perturb a little bit your control U by another one V, then at the limits you get a trajectory that is solution to this linear system. So the most important here result is just to see that this application that's associated to the control state, a trajectory, it's actually differentiable. And then you use the same calculus as I did here for the discrete setting. You just use the differential calculus and prove that this formula, this derivative of the Lagrangian is something that you can express by, with the adjoint states, and the adjoint states, its solution to this equation. So it's here, it's just what you get if you take H, let H go to 0, okay? From this equation, if you let H go to 0, you get exactly this first equation. And this one is now, it's a little bit different from what you have here, because now I have also a state constraint, okay? So I have one more Lagrangian multiplier associated to this final state constraint, and lambda 0 is this multiplier that takes a value 0 or 1, depending if your constraints are qualified or not. So usually in optimal control theory, of course, the Lagrangian is very important as any optimization problem, but there is also another object that is very important and very used in control theory is called the Hamiltonian. So the Hamiltonian is just this product. So here you see everywhere I have the product of the adjoint state with the dynamics f. So this function is what we call the Hamiltonian, and this is something we will use every day during these lectures. So now if I sum up what we had in this optimality conditions stuff, so this is what we get. Assume that we have nice properties on the dynamics, on the cost, everything is differentiable. Then if we have a minimum u bar of the problem, then there exists an associated trajectory y bar, solution of the differential equation. This is by definition of the problem, we note that to u bar we have a trajectory associated and solution to this problem. And we have this additional information. This is now the state equation. And the final information that we have here, look at this condition we have here. We have exactly the derivative with respect to pk of h, uk, and pk. So just to be consistent with the notations, I'm sorry, here this is, we should put bars everywhere. Okay, so with the definition of the Hamiltonian, you can see that this inequality means that the derivative of the Hamiltonian, as we defined, the derivative of the Hamiltonian with respect to the control UK, sorry about that u minus UK bar is positive for any u in capital U. And this is what I wrote here. So this was in the discrete sitting at every time tk. But for the continuous sitting, it's satisfied for at any time t. Okay? So this is what is called in the literature Pontryagin principle. Pontryagin was a Russian mathematician. So I told you that today I show you what the Russian school came up with, and this is the main result that we can refine a little bit more and change the final conditions. So if you look again to what we had here, so this is the derivative of h. That u minus u bar is positive. It suggests that the control is the minimum of the Hamiltonian. And in fact, it is. We don't need any convexity. More convexity. We can prove that the control, if you fix the trajectory, so this should be y bar. If you fix the trajectory and the adjoint state, if you have a wizard that gives you the trajectory and the associated adjoint states, then the optimal control at each time, the optimal value, is the one that optimizes the Hamiltonian along this trajectory and along the adjoint state. Okay? So sorry for this misprint. It should be y bar. So this is the information we have. And in some cases, it's very efficient in the sense that knowing, no, this is not what I want to show. Just a very simple, sorry. I have a simple example that I would like to write down, and then we can solve this example together. Oui. Okay. So the problem I suggest you to consider now is this one. So we would like to minimize this cost involving the final position, and this is the distributed cost that's involve only the control, okay? And the trajectory obeys this simple equation. So we start from any initial condition x is 0, and that's it. And u of t, we assume that we have all the resources that we want. So ut is in R, okay? So u is in R. Y is a solution to this differential equation. What I would ask you now is to tell me how to define the Hamiltonian, and then we can write the optimality conditions and see how they can be helpful to derive the solution. So first, does someone have a guess what is the optimal solution here? It's not a fair question, because I think honestly for a first lecture it's not easy at all to guess what is the solution. Okay. So are you ready? So please, how can we define the Hamiltonian function? So remember, the Hamiltonian is just the product between Q, that plays the role of the adjoint states, and the dynamics. So very easy. Then it's Q, we're in dimension 1, then the scalar product is just a usual product in R. It's equal to minus x plus v. Okay? So this is the Hamiltonian. And now the adjoint state. So the adjoint state is minus p dot t is the derivative with respect of y, which means that here is minus p t, and p, capital T, do you remember? So this is the form. So this lambda 0 is equal to 0 or 1 depending on the qualification of the final state constraints. But here we don't have any final state constraints. Then lambda 0 is equal to 1. And lambda doesn't show up in the optimality condition for this problem because we don't have any final state constraint. Okay? So then P capital T is just the derivative of the final cost. So what is the result then? Can you help? Don't be shy. Just give a guess. What is the final cost here? The function phi here equal minus x. Okay? So this is phi y capital T. This is the final cost plus the integral of L dt. Okay? So here we have P at capital T is the derivative, which means it's equal to minus 1. And now the Pontryagin principle and now I see that I developed the theorem in the case where we don't have this distributed cost. So if we have the distributed cost, and I'm sorry about that, I forgot to say that the Hamiltonian should be this plus L xv. So if you take exactly the proof, add the distributed cost, and you would see that here you so the Hamiltonian is defined by this scalar product plus the distributed cost. Sorry about that. So the Pontryagin principle says that the derivative with respect to u of h along the trajectory y, u, and the costate p. Actually, here the derivative with respect to the control is equal to 0, okay? Is equal to 0 because I have the control in R, so no constraints on the control. Can I use this part? Can you see? Okay. So now I continue here and just write the derivative of the Hamiltonian with respect to u, and it is equal to p t plus ut to ut is equal to 0. Okay? So this is just the derivative with respect to. So what says the exactly the Pontryagin principle is the following: if u, y, p is an extremal then y is connected to u by the differential equation. The adjoint state is solution to this differential equation here. And we have an information linking the adjoint state and the control, and saying that the control law is given by this formula. So this is an explicit formula, and you can solve it exactly because in this situation, in this very particular situation, we know if you solve this differential equation, of course, I chose a simple example where you can do all the calculations. So usually it doesn't happen like that, but this is a very simple situation. When at the first glance, it's not very easy to guess. But if you write the theorem, this is what you get. P de t is equal to the exponential of t minus capital T, if I'm not mistaken. Okay? Maybe there is a minus somewhere. Sorry. Just check my notes. No. Okay. Apparently, it should be something like that. Okay? And then the optimal control is just 1/2 the exponential of capital T minus T. And that's it. So here, by using the Pontryagin principle, you can obtain the analytical solution. But this is just an easy situation where all the calculations can be done. So I think I will stop this part here. Do you have any questions or comments? The first one, this one? It's just when I derive the Hamiltonian with respect to the control. So this is the expression of the Hamiltonian for any x, for any v, for any q. Now you derive the Hamiltonian with respect to its second variable, and you apply it along the trajectory control and costate. And then you get this one. Okay, so maybe we can then stop here, and we meet again in 5-10 minutes in the room.
Let's respect the traditions of IMPA.
Okay.
Everybody goes to have coffee now.
Oh, I'm very respectful.